But it's not live also. Okay, it's live now. That's what he says. Okay, that's good. So at least we can start right now. Okay, but this camera, I don't like it, so. Yeah. Okay, just make sure you pull the right plug and record it in some other way, and then we can merge it later. Okay. Okay, sorry for the delay. I guess let's get started. So we're going to continue. You can hear me in the back, right? Okay. Okay, we're going to continue microarchitecture fundamentals today, and hopefully we're going to finish single cycle as well as multi-cycle microarchitectures. Hopefully it's going to be fun. And next week we're going to start pipelining. So let's get started. So remember, this is your deadline. Today is the deadline for this lecture video. If you haven't done it, this is your chance to get, let's say, easy extra credit. Let me get rid of this. Okay, and then there's one more coming up. And we've started covering microarchitecture. We're going to cover that for many lectures going into the future. And then we're going to get back to ISAs a little bit also. So it's going to be a lot of fun. Please turn off this. Somebody who's on Zoom, please turn off the admitting feature also, because it's very disruptive. We should not have it in the, I'm talking to TA, sorry. We should not have it in the in this course. Okay, so these are the readings. So this is what we were talking about. So I'm going to get to it very quickly. Remember, we were building a very basic instruction processing engine, a computer essentially, and a single cycle machine basically. Each instruction takes a single clock to execute, and only combination logic is used to implement the instruction. There are no intermediate programmer invisible state updates. Later today, hopefully in the second half of the course, we're going to change that. But let's build this machine first. We have an architectural state, process instruction step, happens in only one clock cycle, and at the end, the instruction produces, or the processing in the machine produces architectural state prime according to the specification of the instruction. Right? And remember, this is what happens in the process instruction stage, if you will. It consists of multiple steps, and you've seen this many times. And we're going to build a single cycle machine. All of these 6 phases of the instruction is going to take a single machine clock cycle to complete. Later, we're going to see this multi-cycle machine where we will take multiple machine clock cycles. Each of the phases will take multiple machine clock cycles to complete. This is all a review. You've seen all of these slides before, actually, yesterday. Okay. But basically, this is what we're going to build. A single cycle machine, a combination logic, sequential logic. It's a finite state machine. And we're going to implement each instruction over here, each instruction that we care about. And remember, I also made a distinction between data path and control signals in multiple lectures. Data path consists of the elements or hardware elements that deal with and transform the data signals. Control logic consists of hardware elements that determine how the data path elements should treat the data, basically. What should they do to the data? And we're going to see both of them in action, let's say. And data path elements, if you recall, functional units, hardware structures like muxes, wires, decoders, tri-state buffers, and storage units like registers and memory. Control logic consists of essentially control logic that controls every single one of them. So basically, if you really want to build a machine, you need to provide both the data path and the control logic to execute all ISA instructions that you're supposed to implement, that basically you promised to the software, right? And this is what we're going to build. In fact, this is not going to be complete. As you can see, even some instructions are omitted, but there are even more instructions omitted that are not shown over here. So at the end of the first half of this lecture, hopefully we will have this complete. And it's going to be easy because you've seen data path elements before. We're just going to build it from scratch like we started doing yesterday. And this is what your book has. So your book has something very similar to what I'm going to cover. This is from one other book, Hennessy and Patterson. And this is from your book. Well, if I can get to it. Sorry, something is very slow here. This is from your book, basically. I'm going to cover your book when we talk about multi-program, multi-cycle and multi-program machines. Does that sound good? This doesn't look scary, right? Okay, it may look scary, but it's not that scary because we're going to see the components of it, and you kind of see the components. And once you start understanding how these different components behave, you can guess what's happening in this machine, actually. Okay, so this is what we did. Actually, we did one instruction yesterday. So basically, we're going to start building this data path for arithmetic and logical instructions. And this was the instruction we covered yesterday at the very end. So I'm going to go through it again. Basically, this is the R-type ALU instruction, which is essentially register to register add, you add two source registers and put the destination register into RD, and there are specifications. You can see some bits are specified to be RS, RT, two source registers, and RD, which is the destination register, and then this is the funct field. If you remember, this is the opcode field. Basically, the semantics of the instruction looks like this. If the memory location pointed to PC has this instruction encoding, then general purpose register RD should get the contents of general purpose register RS added to them by the contents of the general purpose register RT. PC should also be incremented. And we did yesterday this basically. What data path elements do you need for this? Well, you have program counter already. We start with the program counter register file registers, and you have the. Can someone turn off the? Can one of the TAs turn off this admitting button? That's very disruptive. We should not have it on in the future. Okay, so you have the PC and PC plus 4. Basically, you have an adder that takes PC and adds 4 to it, right? And then PC plus 4 gets written to PC. Remember, here, we always write to PC at the end of the clock cycle because it's really a finite state machine, right? At the end of the clock cycle, we write, and this is a single cycle machine. So at the end of the clock cycle, all of the updates that are prescribed by the instruction should be done at the end of the clock cycle. This is single cycle. In multi-cycle, we're going to change that. We're going to have a write enable data control signal for the PC program counter also, as you will see in the later part of this lecture. So this is the data path element you need for a PC plus 4, basically. Then you go through the instruction specification and look at, oh, this is the other part. We need a data path element to enable us to do this other part, which means that you add 2 general purpose registers. So we have the register priority. We need to supply the PC to the instruction memory so that we can get the instruction. And the instructions, different fields, different parts specify the source register, 2 source registers in this case, 1 destination register. And register file provides us the values, contents of the source registers, as you can see. And we need to have an ALU that adds those contents, as you can see over here. And we need to connect the result of the ALU to the write port of the register file, and so that we can write the data to the register that's indicated by write register, which is basically indicated by the fields by bits 15 through 11 of the instruction. Hopefully this makes sense, right? Because this is all specified by the instruction. If you go back to the encoding, this is destination register. This is bit 15 through 11. It's not written over here, but you can calculate it, right? It's really bit 15 through 11, this one. And RT and RS are, you can see bits 20 through 16 specifies RT, and bits 25 through 21 specify RS. So there's no magic, basically. You fetch the instruction from memory, you get 32 bits, and some bits are used to index source registers, and some bits are used to index the destination register. You know, based on the opcode of the instruction, that ALU operation should be add, right? So basically, there are 2 control signals that we need to execute this add. You can see one is what should the ALU do? Well, the ALU should do add based on the opcode and the function. Opcode is 0, and function is, in this case, 32, as you can see. By decoding these, which is not shown over here, by decoding these, you need to ensure that these control signals do what add is supposed to do. And also, add needs to write to the destination register, so you need to set the control signal of this destination register write to 1, so that you actually, at the end of the clock cycle, the destination register gets the value coming from ALU result. Does that make sense? So hopefully this is clear, because I am spending some more time on this one because we're building a data path. But it's really not that different from what we have seen earlier in the earlier lectures. Now we're building the full data path, though. This is the complete specification of the instruction. We're doing everything the instruction suggests. Okay, so this was R type. R type means register type, and the format of the instruction looks like this, actually. We're going to look at some other instructions soon. So, okay, this is ALU, but there's also, what does the ALU do? Remember, actually, this is what we have seen earlier. This is the MIPS, simplified MIPS ALU. So addition should be specified as 0, 1, 0. So those ALU operation bits should specify 0, 1, 0, such that the ALU does the addition to its source operands, as you can see, or source inputs. Okay, let's add one more instruction to this. So now let's take a look at I-type ALU instruction. This is still add, but it's an add register plus immediate, right? So this is the semantics, as you can see. Still, we get PC plus 4 because it's sequential execution, as we discussed. And this is the addition specification. General purpose register specified by source register gets added to sign extended immediate field coming out of the instruction. and the result gets written to general purpose register specified by RT. Okay, it was RD before in the previous case. This is RT, so some other bits need to be supplied as the address of the destination register, as you can see. So we'll see how to do that. So if you're just implementing, what happened? Yeah. So basically, this was register to register add earlier. We actually had this, but now we need to add a register. So everything else is still the same, right? The different part compared to the register to register add is you take the source register over here, you add it to sign extend immediate, as you can see. And sign extend immediate comes from the bottom 16 bits of the instruction. You sign extend it and make it 32 bits and add it. So now ALU needs to have some other input, not the register input over here that we had for register to register add. We need to have an immediate input over here. So I'm going to now change things a little bit. Oh, what's going on? Something is going on with my computer. Okay, you can see now, if you want to execute both R-type and I-type ALU instructions, we need to have a multiplexer over here based on the type of the instruction. If it's I-type, meaning if it needs to use an immediate, you should select the sign extend immediate as a second source input to the ALU. If it's not I-type, then the data path should select the register output as the input to the ALU, as you can see. So we needed to add a MUX to support both types of instructions in the same data path. And there's also one more MUX multiplexer you need to add, as you can see over here. This is kind of what I mentioned. The destination register for I-type instructions is specified by bits 20 through 16 of the instruction, as opposed to bits 15 through 11 of the instruction, just because of the way instructions are encoded. So if I go back, you can see that there is no RD here, which used to be here in the R-type instructions. Okay, so basically, by just adding 2 MUXes plus the sign extension for the immediate bits, we can support I-type instructions additionally to the R-type ALU instructions. And this is actually true for all of the ALU instructions. I just showed this for add, but that's true for AND also. That's true for some other instructions as well, like NOR. You can convince yourself by looking at the MIPS ISA. Does this make sense? Okay, I see heads nodding. That's good. So this is good. This is how we constructed the data path. And this is also, as you can see, we are also adding control signals. We're not just constructing the data path, but we're also adding some control signals. So for example, we needed to add this is I-type control signal. We're going to name these as regdest, for example, and ALU source later on. Basically, these control signals will be defined. We're going to generate the control logic based on which instructions are executing. So these control signals are set based on the instructions that are executing. If the instruction is I-type, you basically select the control signal for this MUX such that it selects the sign extend immediate, and the destination is selected by the bits 20 through 16 over here. And ALU operation is selected based on the funct field and the opcode. Okay, any questions? We're going to basically add to this data path more. So remember, actually, just to show you that we're not actually talking about something completely different from before. We actually saw something like this in LC3. Remember, we had the register file, and LC3 had register to register add as well as register to immediate add. And we supported both of them in LC3. Basically, one source register, one source of the ALU is always coming from the register file. The second source can come from the register file or a sign extended immediate in LC3. And remember, instruction register bit 5 was the one that made the difference over here. If the bit 5 was set to 1, we would get the sign extend immediate. If it was not set to 1, we would get the destination source register, second source register coming from the register file. And add function needs to be specified. So you can see that there are some universal similarities between different ISAs because you need to support these basic operations in general. Add, register to register, add, register to immediate. Okay, people remember this one, right? From a couple of lectures ago. Okay, good. Okay, so now let's take a look at data movement instructions. We've actually seen this in LC3 also, but we're going to now do the full thing in MIPS. So this is a load instruction, very similar to LC3's LDR, basically base plus offset encoding. What does this instruction supposed to do? What is it supposed to do? Basically, it increments PC just like every other non-control flow instruction. It basically computes an effective address based on accessing the register file using the space register, adding to it a sign extended 16-bit offset, and then accesses memory using this effective address and writes the result into general purpose register specified by RT, which is encoded as part of this part in the instruction. Ignore this translate part for now. MIPS actually specifies translate. It's due to virtual memory, which we will talk about in lecture 25. There's still time for that. So we're going to ignore this translation issues, which is going to be very interesting going into the future. Okay, so let's implement this now. So what kind of data path? Oh, sorry. So what kind of data path do we need? If you look at this, actually, load is very similar to an I-type instruction. In fact, it's an I-type instruction. The fields are exactly the same as add immediate that I showed you earlier. Here you have RS, RT, immediate. Here you have base, RT, immediate, essentially. So the encoding is exactly the same. That's why this is called an I-type instruction also. So we're going to utilize the data path that we developed for the I-type instructions, which also executes R-type instructions. But now we need to add more. Basically, we already have the logic to do PC+4. Now we need to compute the address somehow. How do we compute the address? Basically, we access the base register, first register over here. That gives us the value of that register. And then we need to have the sign extended immediate, which we already have based on the I-type instruction that we added. And we have an add, we do an add over here. That gives us the LU result, which is our address at this point. So whenever you do add I, you compute a result by adding source register to a sign extend immediate. For load, you reuse the exact same thing to compute an address. Now, what do? That address needs to go to memory. So we connect it to the address port of the memory, as you can see. And we set the memory such that we don't write to it, because load is not supposed to write to memory, as you can see. So we need some signals, control signals to control memory. We set the memory so that we read from it. These signals are not necessary. It depends on your memory. Well, write signal is necessary, but read signal is not necessary. It depends on your implementation of memory, right? A good reason to have a read signal is so that you can save energy if you're not accessing memory, right? You can also say, oh, I always access memory and I always spend energy. But if you have a read signal that's not enabled when you're not accessing memory, you can save energy. Okay, this part I've already said, we already covered actually, because this load word is also I-type. Write register is specified by these bits that are coming from RT, if you will, which is essentially similar to add immediate, as we have seen. Now, once we access memory, we get some data. Where do we put it? We put it into the register file. So we need to connect the memory output, read data output, into the write data port of the register file. And we need to ensure that reg write signal is set to 1 so that we can write to the register file. So this is all you need to execute a load word. Does this make sense? Okay, good. I'm spending still a lot of time. We're going to go faster in the future. So this was load word. That's nice. Let's take a look at store word. Store word is very similar, actually. It's I-type also. Look at the specification of the instruction. It's exactly the same as load word. It's exactly the same as add I. Semantics is different, of course. Semantics basically says calculate the address exactly like we did for load word. But instead of reading from memory, write to memory, the register that we have read, RT. So RT is a source register right now, not a destination register in store word. So we're going to change the data path a little bit so that we can write to memory by reading RT. And this is what will happen. So basically, we're going to write to memory, as you can see. Let's set the control signal appropriately. We're going to not read from memory. We're going to compute the address exactly the same way load word computed it. Basically, base register, the first register, plus sign extend immediate, right? So we access memory. This is the address that we're going to write. So where's the data going to come from? It's going to come from the second register of the register file. So we need a connection. And that's our connection, right? This is RT, I-type, specified by bits 20 through 16. And we read the register file and get the data that we're going to write and connect it to the write data port of memory, and set the write enable signal to memory, mem-write signal. And that's it, basically. That's what store word needs to do, because it's not going to update the register file. So you need to make sure that you don't write to the destination register. This register file write signal should be set to 0. Does that make sense? I just slightly modified the load word data path, basically. Of course, load word had this connection over here, and we wrote to the register. Okay, so now we know how to do load and store. Now let's combine them. This is load store together, basically. Essentially, you need to have the connection from the second register to the write port. You need to have the connection from the read port of the memory into the register file's write port. And a memory write signal is set if the instruction is a store. Memory read signal is set if the instruction is a load. And memory register write signal is set if the instruction is not a store, meaning all of the operate instructions also write to the register. Basically, stores and jumps, some jumps at least, are ones that do not write to the register. Does this make sense? Okay, good. So this is load store. So, but this doesn't completely do the ALU operations also, because what is it missing? So with this data path and control signals, you can completely execute load store, but not the ALU operations, because there's one path that's missing. Remember, when we did the ALU operations, add register R type or I type adds, you need to have a path from ALU result to the write data port, right? To the register file, so that you can write the ALU result into the destination register. Well, how do you add that? Now, how do you merge the load store data path with the data path that executes operate instructions like adds? That's the next slide, if it can come. Basically, that's this. You need to have a mux multiplexer based on the instruction that selects the ALU result or the output of the memory data, so that you can write to the register file. And this mux is controlled by whether the instruction is a load. If the instruction is a load, you take the data you read from memory and write it into the register file. If the instruction is not a load, then you take the data coming from the ALU result and write into the register file, of course, if it's not a store. Right? Does that make sense? So now this data path can execute all non-control flow instructions that we discussed. Load, store, add with registers, and add with immediates. Now we're getting somewhere. And you can see that control signals are amplifying. Now we have another control signal that we added, mem to reg over here, another multiplexer that we added. But we're extending the data path so that we can execute more instructions. Sounds good? Clearly, if you need to add more instructions, you need to, this is actually how people build machines. If you need to add more instructions, you add more data path elements to execute the instruction. As much as possible, you minimize the data path elements that you add, because you already have a data path for some instructions. And then you add more control signals to ensure that the data path operates correctly. Okay, now let's talk about control flow. Now we're going to deal with the program counter part of the machine a little bit, but we're also going to use some other parts of the machine to calculate the target addresses, for example. So this was a simple control flow instruction that we had, jump, and it was J type. This is different from the I type and R type, because look at the formats, right? You have 6-bit instruction encoding opcode and 26-bit immediate value. And the instruction specifies that you should concatenate top 4 bits of the program counter, incremented program counter, with 26 bits of immediate, and the last 2 bits should be 0. So you need to do some bit shuffling such that you do concatenation of these different fields. It's very easy to compute this target, and then program counter gets the target. It's an unconditional jump, basically, to that target address. And okay, ignore this part for now. We're going to extend it later. It has, I didn't connect everything that we did earlier, but we're going to focus on this part. So how do we calculate the address? That's the first question. But okay, before we calculate the address, we've already built the data path for other stuff, right? Assume that it's the same as the data path that we built earlier. The realization is that jump doesn't access memory, doesn't access registers, doesn't write to registers, and doesn't write to memory. So what should you do in this part of the data path? The answer is do no harm. Basically, a jump instruction, you can look at the specification. It's not writing to a register, so you'd better not write to a register, set this control signal to 0. You'd better not read from memories to save energy in this particular case. You'd better not write to memory for sure, because that changes the architectural state if you do it right. And some of the other parts you don't care, basically. You don't care what the ALU does, because you're not going to use that result. You don't care what this mux does. You don't care what any other mux does over here, because you're not going to use the result. In fact, none of these parts of the data path is involved in the execution of the jump. Some other part is going to be involved, like because we're going to update the PC. So what we're going to do is this. So a PC, normally you would increment it, right? But now jump says, oh, I'm going to concatenate part of the PC with some zeros at the end and put the result into the PC. So if the instruction is a jump, you'd better not do PC plus 4, you'd better do this concatenation. Makes sense, right? Now this is wrong, actually. I mean, what I said is right, but where it's taking the PC is wrong. And this is actually important, because the ISA specifies, fortunately or unfortunately, that PC should be PC plus 4. Basically, if you go back to this real definition, this is the incremented PC. So basically, jump specification says that incremented PC should get concatenated with this immediate and with the 0 bits at the bottom. So basically what we did was wrong over here, and you should be careful when you're designing a processor. Don't do the wrong thing. What we should have done is really take PC, add to it 4, and take this, do the concatenation. Basically, input to the concatenation should be from here. So let me actually show that over here, if I can draw. So basically what we should have done is this. Concatenation input should be here, not coming from the PC. Does that make sense? Oh. Okay. Basically, this is incorrect based on the specification of the ISA. And this is a very common mistake, actually. Unfortunately, this is the specification of the ISA. So you should always be careful when you're dealing with the ISA. You should read the specification correctly and get the right thing from the data path. Okay, hopefully that makes sense. Okay, and then there are also other components of jump. There are other types of jump. This was an unconditional jump, but MIPS also has jump register, for example. We need to be able to execute those. I'm not going to talk about these a lot, but let's go to the next slide actually quickly. A jump register, for example, says memory PC, PC gets general purpose register, the contents of RS. So here, basically in jump register, you need to get, PC should be connected to the output of the register file. So you read the register RS, get the contents, and load them into the PC. So there needs to be another connection over here to support jump register. And of course, this mux becomes wider now. So you need to, if the instruction is a jump register, you should select this input to the PC. Make sense? So basically, as you add different kinds of jumps, you need to add different kind of connections coming from the data, coming from different parts of the data path, so that you can feed the program counter with the appropriate target address. Let's take a look at another one. Actually, you need to also save the PC in some of these cases. For example, this jump and link says PC gets a target address, similar to how we calculated it for jump, but you also need to save PC plus 4 to a destination register. And for that, you need to have a connection from PC. Again, this is wrong. Coming from PC plus 4, you should be able to save it to the right data port. So things get complicated as your instructions become more complicated, as you can see. I'm not going to show all of these. Your book has some examples, but your book also doesn't go into a lot of detail in terms of different jumps. But keep in mind that you have different jumps and you need to support them in a real machine. Now in your labs, we're not going to go into a whole lot of detail. But in real machines, you will need a lot more complexity. Okay, so and these are some other jumps. These are good for function calls. If you watch the assembly programming lecture, for example, you need this sort of jumps with linking so that you can do function calls. Okay, so if you want to go more about the, basically, if you really want to implement a MIPS machine, you need to implement every single instruction, just like we discussed. And this is not complete, I think. I'm not sure if this is complete. There's a core instruction set. There's core, basically. It doesn't have the complete instruction set. So there's also floating point instructions that, well, they're also here, but basically you need to support every single instruction, which means that your data path will become bigger and bigger, and your control signals will become more and more. But the process that I've just described is essentially the same. You add data path elements to support the instruction, whatever data path elements they may be, and then you add control signals to support the instruction, and you make sure everything works. Sounds easy, but with a complex instruction set, it gets bigger and bigger. Okay, so let's take a look at conditional branch instructions, and then we're going to be done with the basic data path. Conditional branch instruction, branch equal, remember the branch equal? It is I-type, actually, that's nice. But basically what it does, this is the semantics. You calculate the target address, it's PC plus sign extend immediate, 16 bits, shifted left by 2. If general purpose register contents of RS equals to contents of RT, then you use this target address and load into the PC. If that's not the case, PC gets PC plus 4. And there are variations of it that you also need to implement. But let's take a look at this branch equal. Okay, something is going on. Okay, so basically, how do we execute? This is an I-type instruction, so that's good. It's going to be very similar to the I-type instructions. I'm not going to complete this completely, but what we will need to do is read source register, read the second source register, read both source registers, subtract them from each other, and if the result is 0, then that means that they're equal. So there needs to be some control logic that checks whether the result is 0. And if the result is 0, then the PC should get a value that's specified by the instruction. And that specification, if we go back to it, is PC plus sin x and immediate times 4. So where is that? So we have the program counter. Actually, it's incremented PC again, so you need to be careful. So incremented PC plus 4, plus sin x and immediate coming from the instruction, as you can see, and add them together and put the results into the program counter, assuming branch is taken, meaning this multiplexer is controlled in part by this condition that's coming out of the ALU. So the ALU should check whether the source register and destination register are equal, and if they're equal, and if this is an instruction that checks branch equal, if this instruction is branch equal, then you take the target address that's computed over here and place into the PC. So this multiplexer is controlled by partially the instruction opcode and partially the result that's generated by the ALU, because you're dependent on the branch condition, as you can see, right? And of course, everything else is do no harm. So don't forget to do no harm. If the instruction is not modifying a register, destination register, don't write to it. And we're not even showing the memory over here, because this instruction has nothing to do with main memory, right? So basically, you should not read from memory and write from memory as well. So this is for you to finish and think about. Again, you need to watch out PC plus 4. Even I was making the mistake, right, when I was speaking. I said you take the PC and add to it sin x and immediate. It's really PC plus 4. Okay, so you can think about this a little bit. Okay, something is very slow in my computer. Maybe it's this thing that I'm using over here. So putting it all together, now we actually have all of this. Of course, the finished part. We've seen all of these operations, and this is the control logic. We're going to implement the control logic in a little bit. And it's going to be easy, actually, because it's a function of the opcode plus some things that we generate dynamically. For example, the if it's a branch instruction, conditional branch instruction, the branch condition determines the control signals going into the multiplexer that controls the input into the program counter, right? But this is what we have seen, actually. It's a cleaner version of it, because we were constructing it while we were going through every single instruction. Okay, any questions? Okay, now let's go through the single cycle control logic. So we construct the data path, we've added the control signals, and let's add the control signals. This is actually going to be easy in this particular case, because we have very few instructions, a small number of instructions, and we're going to create this control logic as a combinational function of the instruction that we're going to process. And we're going to look at these instructions, load, store, basically things we have looked at. We're going to ignore the complicated jumps, if you will. Okay, so basically we're going to look at how to generate these orange colored control signals, meaning what you should put in this control box, if you will. And this is a process where you go through every single control signal, every single bit of the control signal, and figure out which instruction should assert it or deassert it. So let's take a look at this register dest, for example. This is this multiplexer over here. This is the register dex multiplexer, if you remember. For R-type instructions, you would select the destination as instruction bit specified by 15 through 11. For I-type instructions, it should be 20 through 16. And that's the idea, basically. And equation is, if you look at the opcode, R-type instructions are 0. Basically, you take the destination register comes from instruction bits 15 through 11 only if the opcode is 0 for the instructions we consider. And now you know how to generate a combination logic for this. You check the opcode. If the opcode is equal to 0, this bit is set. If it's not equal to 0, this bit is not set, basically. Similarly, for ALU source, if you remember, does the second ALU input come from a general purpose register, second general purpose register, or does it come from a sin extend immediate? So let's take a look at that in the data path also. So this is the ALU source, this mux over here. And basically, this is a function of opcode again. Which opcodes are using the second ALU input as immediate? And this is the specification, basically. If the opcode is not 0, if the opcode is not branch equal, if the opcode is not branch not equal, then it should be taken. The second ALU port should be the immediate one. And again, you know the combination logic to do this, right? You can check the opcode compared to you can check the opcode field in the instruction, the top 6 bits of the instruction, and compare it to these values. Okay, one more, maybe we can do one more thing and then we can continue. So this is a mem to reg. Remember this this multiplexer over here. This is the mem2reg multiplexer, actually. It's placed differently over here. Basically, whether the destination register input, the data input is coming from the memory or the ALU result. It depends on, again, the instruction. This is asserted, meaning you select the memory output only if the opcode is load word. Again. Okay, and then you can see if the instruction is writing to a general purpose register, reg write is enabled, otherwise it's disabled. Again, this is solely a function of the instruction, as you can see. So you can generate the combinational logic based on comparison of these opcodes, and these are the other signals that I have not discussed. Well, we've kind of discussed, actually. Memory read, memory write. Clearly, you know which instructions should enable memory read versus memory write, load word versus store word. And then these are the PC muxes that we're going to look at a little bit more when we talk about how to control this machine a little bit more. Does this make sense? So basically now you know how to generate these control signals as well, based as a function of the opcode completely. One difference over here is PC source 2. And here, basically, it's not just a function of the opcode. The opcode should be some branch, conditional branch, and the branch condition should be satisfied. If the branch condition is not satisfied, you should get PC plus 4, as indicated over here. Right? Okay, so let's take a look at, basically, this is our data path. Let's take a look at how to set the control signals. So this is also called microprogramming a machine. We're going to talk about microprogramming at the very end of the course. You have all of these control signals. What should you set them to, depending on the instruction? And if it's an R-type ALU instruction, this is how the control signal should be set to. Basically, this mux should be set to such that it selects this data input. We're writing to a register. Remember, R-type ALU writes to a register, so this should be set to 1. This mux should be set to such that it takes the register input, register file output, second register file output as the input to the ALU, because these are register adds or ALU operations. ALU operation should be determined by the function coming from the opcode, if you remember that function. We're not reading from memory, we're not writing to memory, these should be zeros. And the result of the ALU result should be passed through this multiplexer. So you should set the control signal of this multiplexer accordingly, such that it selects the ALU result to write back to the destination register. And this is R-type ALU, so we should make sure that the control signals of these muxes are set such that we take PC plus 4, which is coming from here, and pass it and write it into the program counter. So that's how we set the control signals. This is R-type ALU. Once you do that, I-type ALU is very simple. So I'm going to go to the next slide. Basically, go back and forth. These are the only differences. R-type, I-type, R-type, I-type. It sounds like fun. So I-type actually selects, as you can see, as we discussed, the destination register from here. You take the sign extend immediate as a second input into the ALU. This part is very similar. This part is very similar to R-type. This is based on opcode because this is a different type of instruction, as we discussed, right? So you can see the difference again between R-type and I-type in this data path. Very little. It's just the control signals because the data path is the same, right? Okay, load word again. Load is writing to a register. It's reading from memory. You need to set the output coming from memory so that this mux actually propagates it into the register file, as you can see. These are the changes that you need. And this should be an add, basically, because you're doing address computation in the ALU and feeding it to the memory over here. And this part doesn't change because this part is modifying the program counter, and you should still get pre-C plus 4 in the end because it's not a control flow instruction. Store word is very similar, okay, but some things don't matter, and you're writing to memory. Basically, you're writing to memory. This doesn't matter because you're not writing to a register, and you should ensure that you don't write to the register. So this doesn't matter. Again, you need to set the ALU function to add so that you compute the address, and the rest is again similar. Okay, this is fun, and hopefully it's clear. Let's take a look at branch not taken. So this branch is going to modify, use control signals up here. Okay, sorry about this again. So branch doesn't do harm to register file and memory. It doesn't write. We need to use the ALU to calculate the branch condition. Based on the branch condition, ALU performs some operation, either a subtract or equality check or greater than or equal check. Actually, the ALU has operations to support all branches. And the branch condition comes from the ALU. And based on that and the type of the branch, you control this multiplexer. So if the branch is not taken, this branch condition becomes 0, meaning it's not taken. So you should select PC plus 4. So that's good. So this is not taken branch. So this shows that some control signals are dependent on the processing of the data. So this multiplexer is in part controlled by the branch condition coming from the calculation of the ALU, as you can see. If the branch was taken, let's take a look at it. If the branch condition was taken, basically, then we should select this part, right? So everything is the same, except the branch condition is 1, and this branch instruction is a conditional branch. So the control of this, the select input of this multiplexer selects the ALU result coming over here. This is different ALU to do the calculation of the branch target address as specified by the conditional branch instruction. Remember, it's PC plus 4 added to a left shifted sign extended 16-bit immediate. Okay, and that needs to be propagated to the PC. Again, this is dependent on the control signals that are generated by the ALU result over here. So there are control signals that are generated purely as a function of the opcode, and there are control signals that are generated based on some calculation that you do in the ALU, especially in the branch instructions, right? But there could be other instructions that require control signals based on some processing. So jump is very similar, except it's easier, if you will, because it doesn't do anything over here, because it doesn't need to calculate a condition, because it's not a conditional thing. It's an unconditional jump. You just need to make sure you don't do any harm over here. But you need to get PC plus 4. This is the correct data path. Earlier, I showed you incorrect one so that you're aware of it, but this is completely correct right now. So you get PC plus 4 and essentially concatenated. This is the concatenated part, basically. PC plus 4, yes, concatenated with left shifted 26 bits of the instruction, and you calculate the jump address, and you need to select that one so that it goes into the PC. So I need to ensure that the control signal of this mux is selecting that this input and not this input, and everything else do no harm. Okay, now we're done actually with the single cycle data path and control logic. Now we're going to evaluate this a little bit. Any questions? Of course, this doesn't contain hundreds of instructions MIP has. Okay, what's in that control box? Basically, we've assumed that it's hardwired control. And this is a good assumption for a single cycle machine, but this may not be a good assumption for what we will see later. So if it's combination logic, purely combination logic, like we have assumed, purely as a function of opcode plus some branch condition bits, then control signals are generated combinationally based on bits in the instruction encoding. So I say control box over here. What does that mean? This is this control box over here, basically. But you may also have sequential logic. You may have a memory structure that contains the control signals associated with an instruction. You index the memory using the opcode and funct bits, whatever. This is called a control store. And after indexing this memory structure, you get all of the control signals that you need. And this is another way of implementing that control box. And we will see this toward the end of today's lecture, hopefully. And both types of control structures can be used in single cycle processors, actually. But we choose hardwired control since it's easy to implement in this case. Okay, and this is basically what does the choice depend on? Again, depends on the trade-off, the latency of each structure, and how much on the critical path control signals are. We will see the critical path of a single cycle machine. Control signals are one of the few things that you need to worry about in that case. But this is our complete single cycle processor, omitting some instructions still. And this is completely correct, actually, based on the specification of the instructions. So if you need to refer to something that's completely correct, this is it. And your book has another single cycle MIPS processor, and I would recommend you take a look at it and also look at the backup slides. I also have a lot of backup slides that look at that are basically constructed based on your book. It's very, very similar, basically, to what I discussed. So you can see that it's very similar. The control signals are essentially the same. They're even named the same, but I'm not going to go through it. But you can go through this by yourself. Basically, if you want to construct a load word data path, for example, it's very similar to what we have done. Okay. And the control logic is essentially very similar, and your book talks about this in detail. So if you want to reinforce what we have learned, go to your book and take a look at it. And this is the other complete single cycle processor from your book, very similar to what we have discussed. Okay, so these are the readings that I would recommend you to take a look at to reinforce these topics. And backup slides actually contain a good chunk of your book. Okay, so this is what we developed in the lectures. This is what in your readings, basically. Let's evaluate this and then take a break. So evaluation is important because it will show us that the single cycle microarchitecture is not that great, basically. Let me actually kind of get you to think of it critically. We've kind of talked about this, but the question is this a good idea? Is it a good design? Anybody? The single cycle processor? So some people are nodding their heads, yeah, or shaking their heads, and that's correct, actually. When could this be a good design? Maybe that's another question to ask. Like, could this be a good design under some conditions? And I'll talk about that. It could be, actually. If all instructions take the same amount of time, this could be a good design, because you're forcing all instructions to go in a clock cycle, and your clock cycle now becomes long. But if all instructions were magically taking the same amount of time, maybe this would be okay. When it's a bad design, well, if instructions take different amounts of time, this is actually a bad design. Then the question will become, how can we design a better microarchitecture? But let's talk about performance analysis to analyze this. So this, remember, this is actually something we discussed yesterday also. This is the execution time of a single instruction, cycle per instruction times clock cycle time. And this is the execution time of the entire program, summed over all of the instructions in the program. And this is another way of looking at it. I'll go through this relatively quickly because it's saying the same things for your benefit. When you're following the lectures, you can actually read them if you're interested. So cycles per instruction is how many cycles an instruction takes, and clock cycle time. Something is wrong, and why is it? It's going very fast for some reason. But maybe I should use this, but that's also not working. Nice. Basically, how long is one clock cycle is the critical path of the logic, and 1 over clock period is your clock frequency, basically. So as a general formula, we have this: number of instructions times cycles per instruction times cycle time. And you can think of cycle time as 1 over frequency of the machine, basically. And all of these slides are showing what I earlier said. So this is our execution time. Now, if you look at the execution time of a single cycle design that we just designed, every instruction takes 1 cycle to execute. CPI is equal to 1. Cycles per instruction is equal to 1. Basically, there's no difference between instructions. How long each instruction actually takes is determined by how long the slowest instruction takes to execute. Because we know that not all instructions require all parts of the machine, right, as we have seen. Some instructions require some more processing. So you need to make your cycle time such that it's long enough to execute the longest possible instruction as it's going to take, even though many instructions may not take that amount of time. So that's the downside of this design, basically. As a result, clock cycle time of this microarchitecture is determined by how long it takes to execute the slowest instruction. And let's take a look at what that slowest instruction is. Basically, critical path of the design is determined by the processing time of the slowest instruction. So what is the slowest instruction to process? Anybody? Yes. Say it again. Well, in this case, we don't have multiplication here, right? But it could be, yes. If the multiply takes a long time, it could be integer multiplication. But we're going to look at it within the context of what we have seen. So that's good. So basically, we're going to look at which instruction. So the question is, does every instruction take the same time latency to complete? And the answer is already no, because they don't go through the same parts of the data path, right? So let's find the critical path in our data path. This was our processor. Let's take a look at the critical path. So assume for this design, instruction fetch takes, let's say you access memory, it takes 200 picoseconds. Instruction decoder and register file access takes 50 picoseconds. ALU and adders take 100 picoseconds. Register file also takes, well, we already said that. Memory here takes again 200 picoseconds, and write back, register file write takes 50 picoseconds. Different types of instructions require different parts, really. So R type instructions don't require memory, for example. I type also don't require memory. Load word requires everything. Store word doesn't require register file write. Branch doesn't require memory or write back. And jump is very easy, as we have already seen. So if you actually think about it, you will see that, and we're assuming other logic and wire delay, muxes, for example, are 0 picoseconds. So if you look at this like analytically, you will say, okay, load word takes 600 picoseconds. And that's the longest instruction. But if you're executing a jump, it's 200 picoseconds. Well, too bad. You're allocating a single cycle to execute all possible instructions. So your critical path is 600. So your clock frequency is determined by the slowest instruction in this particular case. Make sense? So you can also find the critical path. Let's go through this quickly. So if you want to do the R type and I type ALU, what is the critical path? Well, there are two possible. Oh, okay, something is wrong. There are two possible critical paths. You're incrementing the program counter. It takes only 100 picoseconds. But for the rest, you need to access the memory to fetch the instruction. You need to access the register file. So accessing memory 200 picoseconds, accessing the register file 250 adds 50 to it. ALU operations adds 100 to it. And then writing to the register file adds 50 to it. So R type and I type ALU critical path is 400 picoseconds. Load word, this is the worst one. You need to access memory to fetch the instruction. You need to access the registers. You need to go through the ALU to calculate the address. You need to go through the memory to get the data. And you need to write back the data to the register file. As a result, it takes 600 picoseconds. This is the critical path. And this part is not critical because it's PC plus 4. Store word, very similar to load word, except you write to memory. You don't take the data out of memory. So it's 550 picoseconds, close by. Branch taken is actually very short. You can do this on your own. The critical path actually goes from the branch condition calculation logic. And it's only 350 picoseconds in this particular case compared to load word, which is 600 picoseconds. And jump is the easiest, as we have also seen, right? It's only 200 picoseconds because it doesn't need to deal with even a register file access over here. So now hopefully we've convinced ourselves that the load word is the longest instruction over here. Okay, so this is really a great place to stop actually. And let's take a break. And then we're going to talk a little bit more about the critical path and then hopefully do better than this microarchitecture. Okay, and we should solve the problems over here because I seem to have some more problems than expected. I don't know. Screen sharing, okay. So I'll stop the video also or no? Okay. Let's see. Okay, shall we get started? So this is where we left off. We were calculating the critical path. Basically, we calculate the critical. Actually, let me pull back a little bit. What we have done is essentially calculate the critical path of all instructions. This was a rough calculation, right? We didn't, for example, we assumed, for example, other logic and wire delay, latch delay as 0 picoseconds. In real life, that's not the case, of course. But we looked at the major structures that we accessed, and even then, even with these simplifying assumptions, we found there's a huge variation in terms of the latency, how long it really takes to execute an instruction. Load word needs 600 picoseconds, jump takes 200 picoseconds, right? But now single cycle microarchitecture forces us to determine the clock cycle time based on the worst case, meaning the longest instruction to process, in this case, load word. If you had a much more complicated instruction, it would be that one. It could take 10 milliseconds. That's why this architecture, this design, this microarchitecture design is not very good. And we're going to talk about that now. So this is the exercise we went through, find the critical path. This is similar to the timing and verification lecture, except it's at a higher level, right? We just basically said, okay, these are the values that we assign to register file, or memory, register file, ALU, other memory, and then we add them up, basically. It's a rough analysis, basically. If you were really designing a microprocessor, you would do this analysis much more rigorously in the end. But this sort of rough analysis is very good to begin with, because it gives you an idea quickly. Okay, there's a huge variation between jump and load word, right? Okay, and we've done this also, and you know that load word actually takes the longest. One more other comment over here. Why am I considering this other path? Because that could also potentially be the critical path, right? There could be multiple critical paths, multiple candidate critical paths, except this takes much longer than this part. And this is the concurrency in hardware, right? These things are happening concurrently. While you're doing this operation to get the registers, add them, calculate the address, access memory, and get the result into the register file, you're also incrementing the program count. Potentially, if you were doing complicated operations over here, this part could have been the critical path, but clearly it's not in this particular case, right? That's why it's good to look at what's happening concurrently and figure out what's the thing that takes the longest among those things that are happening concurrently. And again, this is something we have discussed as well in timing and verification briefly. Okay, store word we've seen, branch taken we've seen. So the interesting thing about branch taken is the control signal over here comes from, or part of the critical path comes from this control signal, which essentially says what is the branch condition? Is it taken or not taken? And this control signal is generated based on the ALU operation that is performed on the registers, right? It doesn't come from the opcode directly, basically. Okay, and jump we've seen. Okay, so what about control logic, basically? So we've been looking at the critical path. Control logic can also affect the critical path, actually. If some of the control signals take too long to generate, that could be part of the critical path. In fact, if this branch taken, you can see that the critical path of the branch taken instruction, just the branch taken, goes from this control signal, branch conditional control signal that controls this multiplexer's select input. Multiplexer's data input is not on the critical path. You can see that it's just generated quickly. This is the data input is what PC plus 4 plus shift left shifted sign extend immediate. This blue part is not on the critical path, but the select control signal is on the critical path of branch taken. It's not on the critical path of the general single cycle machine because branch taken is still too short. It takes too short compared to load word. So basically, control logic sometimes can be on the critical path of the machine also. If it takes too long to generate the control signals, for example, it's possible. And in the past, there have been machines where control stall accesses took too long. As a result, they were on the critical path. But in general, if you design a good machine, your control signals, you should hide the latency of control processing as much as possible. And we will see that much better in the multi-cycle machines, which we will talk about in this part of the course. Okay, so what is the slowest instruction to process? Let's talk about that a little bit more. Because even though things look bad, they're actually much worse, let's say, for the single cycle machine. Why? Because memory is not slow. Memory is not magic, right? We've kind of assumed this memory is 200 picoseconds, right? In real life, as we discussed earlier, it takes sometimes nanoseconds. And potentially, if you're going to disk, milliseconds to access memory, right? So in real world, this single cycle microarchitecture is a terrible fit for the real world. Sometimes memory takes 10 milliseconds to access. Does it really make sense to have a simple register add or jump to take as long as a 10 millisecond memory access plus everything else that you need to do the memory operation? And the answer to this should be obviously no, right? And sometimes you actually need to access memory multiple times to process an instruction, right? Actually, every instruction requires one memory access to fetch the instruction, right? But load word and store word requires, in this particular case, 2 memory accesses to fetch the instruction first and then to fetch the data next from memory. And then that basically multiplies the amount of time that you need to wait for memory. So do you provide multiple ports to memory? You can do that, but it's a sequential process. You need to fetch the instruction so that you can fetch the data, because you need to calculate the address, figure out the registers after you fetch the instruction. So basically, the whole thing, the reason I'm telling you this is because the single cycle processor makes little sense in the real world. It makes basically maybe let's say no sense in the real world. Okay, I got rid of that. Basically, it's very complex. What do I mean by that? Basically, I mean all of these 4 things. It's contrived in the sense that all instructions run as slow as the slowest instruction. The slowest instruction can be very, very long in the real world. It's inefficient because of the same reason, basically. You must provide not only that you need to wait for the longest time an instruction can possibly take for every instruction, but you must also provide the worst case combinational logic in parallel as required by any instruction. This actually increases your hardware cost compared to what we will see in a little bit. For example, because you're doing everything in one cycle, you cannot use the same ALU to do the let's say PC+4, while also using the same ALU to do an arithmetic operation. Does that make sense? You have to have 2 ALUs. One needs to do the PC+4, and the other needs to do the arithmetic operation, because everything happens in the same cycle. You have no luxury to use the same ALU because you cannot, right? Everything is combinational. It happens in the same cycle. But if you distributed the processing over multiple cycles, you could have said, I have one ALU only. That's it. In this cycle, I'm going to increment PC+4 using that ALU. In the next cycle, I'm going to use it to calculate the address. In the next cycle, I'm going to use it to add multiple operands, right? Basically, you can be very frugal, have a single ALU and do different things in different cycles. Whereas here, an instruction requires multiple ALUs to actually execute. You have to provide all of those ALUs. And ALUs are one example on. That's actually one of the reasons why you provided multiple memories also here, because you have to access different memories. Basically, you need to replicate a resource if it's needed more than once by an instruction during different parts of the instruction processing cycle. This is a more formalized way of putting it. That's why you need to replicate a resource. As a result of this, partially as a result of this, well, certainly this is inefficient, right, in terms of complexity of the hardware. But also, it's not necessarily the simplest way to implement an ISA, because now you need more resources. And actually, if your ISA is very complicated, for example, x86 has a string copy instruction. It's called repMoveS, but it's essentially copying 2 strings. You have the start address of this instruction in this memory location, one string in this memory location, you have the start address of the other string. What it does is it compares 2 strings. And these strings can be arbitrary values, meaning the length of the string can be arbitrary. It's stored in a register, basically. So imagine this instruction now. It can have 1 billion characters that you're comparing in each string, and the strings may be equal or very similar at the very end. So this instruction takes a really, really long time to execute, basically. Does it really make sense to design a single cycle microarchitecture for this? And the answer is no, obviously. VAX said an index, multi-dimensional array indexing instruction. Can you really design an efficient architecture where you access memory, let's say 10 times to do a 10-dimensional array indexing? Again, this doesn't make sense. And also, it's not easy to optimize or improve performance because you cannot optimize the common case. So this is one of the principles that we'll discuss in the next slides. One of the big principles in design is figure out what's the common case and optimize for that common case. So if your common case is machine is going to do a lot of add instructions, optimize for those add instructions. Optimize the clock frequency for your add instructions, because you know that 90% of the workloads that are going to execute are going to do add instructions and not loads, let's say. But you cannot do that in this case, because you may say, okay, add is the most common instruction that I see, but it's not the longest instruction. So now you're dictated by the longest instruction to determine the clock cycle time, which is load word in this particular earlier case, right? So you cannot say, I'm going to optimize the add. I'm going to optimize my clock cycle for the add, basically. Because you cannot, because it's single cycle. So basically, it violates this common case design principle, and it doesn't work, essentially. So you need to optimize for the worst case all the time, meaning the worst case instruction to execute, the longest latency instruction to execute. If you want to improve performance, you need to reduce the time it takes to execute that instruction. So now that I've deconstructed single cycle microarchitectures, let's talk about these design principles, and we can compare the single cycle microarchitecture to these design principles. And these are three major design principles. Remember, I told you that we're going to talk a lot about principles in this course, and this is one example. Critical path design, bread and butter or common case design, and balanced design. And single cycle microarchitecture actually violates all of these. The next slide is going to ask you that question, but you can start thinking about this. So what does critical path design mean? Basically, minimize the clock period or maximize the clock frequency as much as possible. Find and decrease the maximum combinational logic delay. Break a path into multiple cycles if it takes too long. Well, you cannot do that in this case because everything takes a single cycle. You have to be optimizing the worst case instruction in this particular case. And it's very difficult to optimize some worst case instructions. Second is common case. We already discussed this, but basically this, the general principle says, spend time and resources on where it matters. Focus your efforts, basically. If 95% of your workload consists of ads, focus your efforts on the ads. Don't ignore the 5% because that could become your critical path or common case if you once you optimize the 95%. But start focusing your efforts by looking at the 95%. Improve what the machine is really executing, for example. So this brings us to common case versus uncommon case. Optimize for the common case and make the uncommon case good enough so that it doesn't become the common case, let's say. Does that make sense? So that's the idea, basically. You cannot do that again, as I said over here, because you're limited by the worst case instruction in this case, in a single cycle machine. And the last thing is balanced design, which is balance the instruction and data flow. Basically, have a nice balanced system that you design. There are no big bottlenecks in the design. Balance the instruction and data flow through the hardware components. Balance the hardware for the work. And I would argue that single cycle microarchitecture is not a balanced design because of the reason that we discussed earlier, which is you have to replicate a lot of resources to ensure you do everything related to an instruction as single cycle. So if you need to access memory 10 times, you need to replicate memory 10 times or have 10 ports to memory. And there are some instructions, real instructions architectures that can access memory 10 times. String copy is one example. In fact, more than 10 times. So basically, it violates, the single cycle microarchitecture violates all these design principles. And this is for you to think about, basically. How does a single cycle microarchitecture fare with respect to these principles? I already gave you the answer in the prior slide. Okay, so if you allow me a little bit, we should also talk about system design principles here, because it's never good to violate these principles. And the reason we cover single cycle microarchitectures is to show that principle designs are actually very important. But there are other system design principles that are important to follow, and people actually documented these when they built systems and architectures. This is true for any system design in general, like real architectures, buildings, and bridges. We actually talked about this at the beginning of this lecture, right? Good consumer products also. You should always have good principles to design good consumer products. So I think a lot of these apply to many things that you do in product design and mechanisms for security and safety critical systems, right? You cannot ignore some safety principles, for example, if your goal is to have a safe self-driving car, which we're very far away from today because we're not really looking at principles in that domain as much, let's say. Okay, so remember the principle design from our second lecture. That's one of the reasons why we discussed Frank Lloyd Wright, and architecture should be based upon principle and not upon precedent, right? Okay, this is just to jog your memory, right? And these are the beautiful pictures, just to relax you a little bit. Okay, so the takeaways is, I mean, this you've already seen as well in the earlier lectures. This is lecture 1 or 2, I don't remember which one. But basically, principles do not change as much. Underlying basic building blocks and design may change. Underlying technology may change, but principles, methods used for design depend on the principles that are employed, and principles do not change as much. So some other system design principles, separately from what we have discussed, include some other things. I will discuss that. But some references that cover these design principles are these. If you're interested, you can take a look at them. This is Yale Pat, my PhD advisor's seminal paper on this topic. If you're interested, you can take a look at it. Mike Flynn, who is a pioneer in computing architectures and computer arithmetic, actually, has some principles over here, like balanced design comes from this beautiful paper. Gene Amdahl, Amdahl's law. This is actually something that I will also assign as an extra credit assignment. It's only a 2-page paper that talks about Amdahl's law. How many people know about Amdahl's law? Okay, good. Now, how many people have read Amdahl's paper? Okay, one person, that's good. Now you're going to review it if you're interested. So this is actually a common thing that I get. Everybody knows about Amdahl's law and nobody has read, well, nobody with approximate computing, nobody has read the paper. So I'm going to ask you to read it. But common case design actually comes from Amdahl's law, basically. Amdahl argued that you should really design for the common case, at least implicitly. And Butler Lampson, another Turing Award winner, actually has this beautiful paper on hints for computer system design, if you're interested. But basically, I'll cover 2 more of these design principles, or maybe 3 more, I don't remember. Well, 2 more, actually. And one is keep it simple. And actually, I would say single cycle microarchitecture makes it very complex by trying to fit everything in a single cycle. And this design principle actually is very commonly known. Somebody said this. Does anybody know who this person is? Everything should be made as simple as possible, but no simpler. It looks like this. Okay, yeah, that's the person. And that's true, I think. And keep it low cost. This is, I don't know who really said this first. It's anonymous mainly, but usually an engineer or a designer is a person who can do for a dime what any fool can do for a dollar. Clearly, this is the American version, right? Dime and dollar. Dime is 10 cents, dollar is 100 cents. Okay, and for more, I would suggest seeing this paper that I also mentioned earlier, Hints for Computer System Design. Okay, so always the question is, can we do better? So single cycle microarchitecture, we kind of evaluated it based on these principles. And the question now becomes, can we do better and how? And we're going to do better, basically. And we're going to ask this question over and over and over and over in this course, basically. We're going to see ideas. We're going to evaluate them. These are the strengths. These are the weaknesses. Here are the trade-offs. And then the next question becomes, can we do better? And what are the new ideas that enable us to do better? And what are the new trade-offs that are enabled by those ideas? This is how science and engineering also works, actually. You always ask this question, can we do better? You never are satisfied with the status quo. Status quo gives you this. Your question always is, can I do better? Okay, let's take a look at it. And that's where basically multi-cycle microarchitectures is one way of doing better, but it comes with its own trade-offs also. And the idea is, I already given you the idea. Let each instruction take close to as much, only as much time as it really needs. I didn't specify the idea this way, but that's essentially the crux of the idea. In single cycle microarchitecture, every instruction was taking as long as the longest instruction to process. Here, we're going to say instructions are different. Let each of them take as much as it takes, as long as it really needs, basically. So the question is, how do you do that? Basically, you need to determine the clock cycle time independently of instruction processing time. Before, we were coupling these 2 things that are actually completely orthogonal, maybe even irrelevant to each other, right? Right now, we can say, my clock cycle time is going to be 100 gigahertz, and I'm going to design a machine that does very well with this. And I don't have to fit an instruction to, let's say, 1 over 100 gigahertz time, right, seconds. Every instruction can take multiple cycles right now. Many cycles, in fact, potentially. So each instruction takes as many clock cycles as it needs to take. Now we have multiple state transitions per instruction. So we're going to design a finite state machine to enable this, or more complicated finite state machine, because a single cycle microarchitecture is also a finite state machine, except it's a very simple finite, well, simple in the sense that you have a state register and combinational logic, and that's it. You have, in a sense, it looks relatively simple. But now we're going to actually have lots of states in our finite state machine and many state transitions per instruction. The states followed by each instruction is going to be different, as we will see. Okay, and recall, we've already talked about the slide, so I don't want to take more time. The single cycle microarchitecture was doing architectural state prime in a single clock cycle. We're going to do it in multiple clock cycles here. So let's take a look at that. You have architectural state at the beginning of an instruction. In one clock cycle, process part of the instruction, generate some intermediate results, store them in some registers that are not visible to the programmer, and then process part of the instruction in the next clock cycle, and then store the intermediate results somewhere. and then keep doing this. And after some point, you generate architectural state prime that is required for you to generate based on the instruction set architecture description of the instruction. Right? So basically, your goal is still get to architectural state prime from architectural state based on the definition of the instruction in the ISA, but you do it in as many cycles as the instruction needs, as opposed to in a single clock cycle that's extremely long. Okay, hopefully that's clear. So let's take a look at, let's evaluate this first before we go into how to design it. So what are the benefits in terms of these 3 key design principles that we laid out earlier? So a critical path design says you should be able to reduce the critical path as much as you can. And here we can keep reducing the critical path independently of the worst case processing time of any instruction. We basically freed ourselves from this worst case latency of a given instruction. Right? We can set the critical clock cycle time independently, basically. Common case design. Well, if your adds are more common, okay, now reduce the number of states, reduce the number of clock cycles it takes to do adds. If some instruction is not common, maybe don't optimize it as much. Right? Now you can optimize your common instructions, right? I just gave you an example of adds, but if your loads are common, reduce the number of states it takes to execute loads, and add the resources to enable that, basically. Balanced design, there's no need to, again, basically, the problem with single cycle was you need to replicate a lot of resources. Here we can be frugal. You don't need to provide more capability or resources than really needed. You can use the same ALU to do PC equals PC plus 4, to calculate the branch target address, to calculate the register results, to calculate the address of the memory. And if an instruction requires all of them at the same time, meaning its specification requires that the instruction should do that, you can do them in different clock cycles on the same ALU. So you can have only one ALU to do all of that. It's very powerful, basically. And this enables you to get to balance, basically. This by itself doesn't provide balanced design, but this enables you to keep things balanced because you don't have to provide the worst case combinational resources that any instruction requires. Okay, so basically this is what I just said also. An instruction that needs resource X multiple times does not require multiple X's to be implemented, right? And it could be register file, memory, ALU, muxes, whatever. So this leads to more efficient hardware. You can reuse the hardware components needed multiple times for an instruction. Okay, and we're going to see that. But again, any idea has upsides and downsides, and this is a big takeaway from any idea we examine. Multi-cycle microarchitectures has those big, good upsides, but they also have downsides. Can anyone think of what are the downsides? I actually said this earlier. Anybody? There's a hardware cost downside, and there's also some wasted time downside. I kind of given it, but basically hardware cost downside is you need to store the intermediate results at the end of each clock cycle, right? Single cycle is nice because there's only one clock cycle and there's no intermediate storage. Here you need to add intermediate storage, so there's hardware cost. So hardware overhead for these registers that are not visible to the programmer. And whenever you're processing things in multiple cycles, remember in timing and verification lecture, we said that part of the clock cycle is wasted. Why is it wasted? There's a setup and hold overhead for the registers. And also there's a clock skew, as we discussed. So basically register setup and hold overhead is paid multiple times for an instruction. And if you execute an instruction 100 clock cycles, you paid 100 times, for example. Basically, this means that a clock cycle, only a fraction of the clock cycle, only in a fraction of the clock cycle you can do useful work. Part of the clock cycle is always wasted due to sequencing overhead, register setup hold overhead, as well as clock skew. Okay, so you can see that there are downsides of multi-cycle design as well. Okay, let's take a look at the performance analysis. Actually, you've seen this slide before. I'll keep harping on this performance analysis. CPI times clock cycle time is the execution time of a single instruction. You sum it up across many instructions to get the execution time of an entire program. So single cycle microarchitecture we've seen before. CPI is 1, clock cycle time is long. Multi-cycle microarchitecture, CPI is different for each instruction. Average CPI is hopefully small, especially if you're doing common case design. If 90% of your instructions are adds, and if you reduce the number of cycles to execute the adds, that's great. And clock cycle time is short. You can say my clock cycle time is 1 terahertz and implement it, right? Okay, sounds good. So basically we have 2 degrees of freedom to optimize independently, clock cycle time as well as CPI. And CPI, you can do the common case. Okay, let's take a closer look at this multi-cycle microarchitecture right now. Any questions? Okay, feel free to ask questions. I got good questions during the break, so let's see. So let's see the closer look. This is actually an old idea, and this is Maurice Wilkes, who was one of the earliest Turing Award winners, and he wrote this paper in 1951, as you can see. He called it the best way to design an automatic calculating machine, and it's a beautiful paper where he talks about this idea of multi-cycle machines and micro-programmed microarchitectures, essentially. And he talks about an elegant implementation of a machine, and we're going to talk about that essentially, at least a little bit more abstractly. Well, maybe a little bit more detail, but he also talks about some other things that we're not going to talk about. But basically, the idea is multi-cycle microarchitecture. And the key idea for realization, as described in Maurice Wilkes' paper, is one can implement this process instruction step as a finite state machine that sequences between states and eventually returns back to the fetch instruction state. So you have a finite state machine, starts in the fetch instruction, and then you go to decode, and then you basically take a different path based on the instruction type and execute through some states, finish the instruction, and you go back to the fetch state again. And we will see that finite state machine a little bit. So that's the idea. Have a finite state machine that sequences through states in multiple clock cycles and eventually returns back to the fetch instruction state to fetch the next instruction. Okay, so a state is really defined by the control signals asserted in it. Every state has different control signals. We've actually kind of seen this earlier. Before we got into single cycle machines, I've kind of given you the finite state machine, right? Now we're going to go into a little bit more detail into the data path. I hadn't given you the data path completely over there, for MIPS at least. A state is defined by the control signals that are asserted in it. And control signals for the next state are usually, as much as possible, determined in the current state. So this helps your critical path also. In a single cycle machine, if you remember, we discussed yesterday, you have to generate the control signals as well as process the data path, and control signals are part of your critical path. Here, control signals can happen earlier in a prior cycle, and you use them in the next cycle, basically. And this is a very important principle for critical path design. Don't let control signals get on your critical path, basically. Okay, so let's take a look at this. So basically, this is what we're talking about. We're going to implement a finite state machine that goes through this instruction processing cycle for every instruction. So let me go into a little bit more detail. We're going to divide the instruction processing cycle into states. And a stage in the instruction processing cycle can take multiple states. So if you go back to this, fetch can take 5 states, for example, or 3 states, or 4 states. And you can stay 100 cycles in that fetch state, for example. For example, there could be a memory access state in that fetch stage, and then you can stay there for 100 cycles, as we will see. So basically, you can accommodate very long latencies this way. Okay, a multi-cycle microarchitecture sequence from state to state to process an instruction. We already said this. The behavior of the machine in a state is completely determined by the control signals in that state, as we have discussed and as we will see. And the behavior of the entire processor is specified fully by a finite state machine. And we will see, we'll construct that finite state machine actually very soon. And in a state, control signals control 2 things: how the data path should process the data, and how also to generate the control signals for the next state or next clock cycle. Okay, and we've kind of seen all of this actually, but now we're going to divide things into multiple clock cycles. Okay, let's take a look at an example multi-cycle microarchitecture. There are multiple examples. In fact, your book, Pat and Patel book, actually has a very nice example from LC3, which we're not going to cover here. I'm going to give you an example of MIPS. We're going to take the MIPS that we kind of constructed, and we're going to turn it into a multi-cycle microarchitecture. And I'm going to use this other, your book's microarchitecture, which is very similar to what we have constructed, actually. You can see the PC source muxes over here. They were over here in the earlier design. You can see the input to the ALU mux over here. You can see, or you cannot see. Oh, this is, they put the mux over here. Yeah, this is the mux that determines which destination register should get the data. This is the mem-to-reg mux over here. So basically, this is the single cycle processor we constructed, actually. Multi-cycle processor, basically, we've already discussed this, so I'll go through this very quickly. Actually, this is for your benefit. What do we want to optimize? Basically, how do we want to design this multi-cycle processor? Single cycle processor microarchitecture uses 2 memories. We can use a single memory right now, right? And access the different parts, and we're going to do that. Single cycle microarchitecture needs 3 adders: ALU, PC calculation, and branch address calculation. We want to use only 1 ALU for all operations. So if you go back, there's 1 ALU over here, 1 adder or ALU over here, and another ALU over here. So we're going to reduce that to 1. And single cycle microarchitecture, as we discussed, each instruction takes 1 cycle. we want to fix that. We already discussed all of these, and this is just for your review. We want to divide each instruction into multiple clock cycles, and simpler instructions can be very fast this way. Okay, let's take a look at how we construct it. So we're going to look at an example load word, which you have seen multiple times. This is what we need to do in a multi-cycle microarchitecture. Well, this is actually true. But you need to do this regardless of the microarchitecture you design, because this is specified by the ISA. But we're going to kind of break it into 5 stages over here. 5 clock cycles, let's say. You read the instruction from memory, and then read register from the register array, add an immediate value to it to calculate the memory address, read the content of this address to accessing memory, by accessing memory, and write the register, write the result into register T0 in this particular case, based on the value that you read from memory, because this is a load instruction. So this is the same load instruction that we've seen. Now let's construct the multi-cycle data path. We're going to break things into cycles. So basically, the first stage is fetch. So we're going to supply the PC to instruction/data memory, as you can see. So you can only have one memory right now. You're going to access it in different clock cycles for different purposes. And then now we're going to access it based on using the PC, and the data that we get is the instruction. And we're going to latch that into a register. So one clock cycle is just used for accessing memory, fetch instruction basically. That's nice. I can determine that clock cycle to be short, right? I don't need to do everything specified by instruction in a single clock cycle. And you have IR writes that's asserted only in this state, meaning when you're fetching the instruction. We're going to use this register to decode and use some values out of it in the remaining cycles to process the instruction. So there's as you can see, there's an overhead register which we did not have before, and we have a new control signal to write to it. Okay, the next cycle, register read. This is step 2. Sorry, you basically take the thing that you have latched in the instruction and access the register file, and latch the result into another register as you can see. And this doesn't need a control signal because it can always be supplied. But later, as we develop the data path, this can increase. Maybe there are control signals. So this is the second cycle. Next stage is also actually concurrently with this, you sign extend the immediate. You don't necessarily need to latch it actually over here, because this doesn't change while the instruction is being processed. You could latch it also, but there's no need basically. That's why there's no latch over here, as you will see. Okay, and then we calculate the address. How do we calculate the address? In the next clock cycle, we take the value of the base register, add to it the sign extend immediate, and set the ALU control to add, and the ALU result gets slashed to another register that we added. Okay, so that's next cycle. Now we've done 1, 2, 3 cycles, right? Now what do? Nope. Basically, we need to do a memory read. Remember, we have only one memory now. Because we can get away with one memory. We don't need 2 memories because we're not single cycle, or we don't need 2 memory ports. We're not single cycle. So what do? We take the address that we just latched in the prior cycle, use it in the current cycle to address the memory. So you need a multiplexer saying whether you're accessing instructions, meaning the address is coming from PC, or the address is coming from the address that's computed by the ALU in the prior cycle. And then input that to the instruction/data memory and latch the result. This is the data that you load in the load instruction. And the next cycle, we're going to write that data into the register. And you can see that this is the data that's coming from the register we loaded in the previous cycle that came out of the memory. We set the register write signal to 1. So control signals are very similar actually, but we added more registers that require more control, as you can see. And the destination register should be this one, indicated by the instruction register that we latched several cycles ago. So we've taken 5 cycles to execute this add now. Sorry, not add, load word. And that's it basically. Well, we also need to increment the PC. So maybe we're going to take 1 more cycle, or we're going to do it concurrently with the prior cycle. But basically, we've used only 1 memory. We're going to use the ALU to increment the PC also. So in an earlier cycle, we calculate the address. In the same cycle, when we're writing the data, we could also increment the PC basically. When we're writing the data from here into the register file, we could also increment the PC. Or when we're not using the ALU, we could also increment the PC basically. So this requires you take the PC, input it as one of the sources to the ALU, in addition to the register, latch register coming out of here, and also input the PC +4 a value of 4 so that the ALU can do the add, and you take the result and latch it to the PC in the next cycle. So this is the last cycle of execution of load. You write the register concurrently, you also increment the PC. But you could have incremented the PC in another clock cycle where you were not using the ALU also. Does that make sense? So with 5 cycles, using 5 cycles, we've executed this load, and we've used only single instruction and data memory, only a single ALU. Of course, now we added some more muxes to make sure that we have the right inputs to the ALU, because we didn't replicate the ALUs, and to the right inputs to the instruction data memory, because we did not replicate the instruction and data memory as separate. So this is beautiful now. By distributing the processing of an instruction across multiple cycles, we not only reduce the clock cycle, we also reduce the hardware cost of this, hopefully, because we're adding some hardware costs like the multiplexers over here, or increasing the size of the multiplexers. But we're getting rid of the big hardware costs like ALUs and instruction and data memory, as you can see. Okay? Okay, that's the beauty of the idea, as you can see. The downside, don't forget the downside, these registers, right? We added this, we added this, we added this, we added this. They're intermediate registers to store the values we latched at the end of each clock cycle during the processing of an instruction. So let's take a look at store word. Basically, once we've constructed this data path, this is for load word, we can add store word to it. Actually, store word is very similar to load word, except in the last cycle, it needs to write the data into memory. And that data to write is already latched in the register, and you need to provide a write data port into memory, and you need to assert the memory write signal. So store word is very easy to add once you've constructed load word. It still takes multiple cycles, but this is the difference in the last cycle, basically. Actually, store word takes 1 cycle less because you're not writing to, this is the stage where load word is reading from memory, and store word would be writing to memory. Okay, that's store word. Now let's take a look at some other instructions. It's going to be easy, basically, to add the other ones. R-type instructions. You need to read from RS and RT and write the ALU result to the register file and write to RD instead of RT, because R-type versus I-type, you remember that distinction. And you need to add the data path element, in this case, muxes, to be able to do that. You need to select the destination register such that it's RD instead of RT. And you have this mem to reg register still, because R-type instructions take the ALU result, latched ALU result, and write it into the register, whereas the load word takes the latched memory output and write it into the destination register. So we need to add this mux to support both the memory output as well as the latched memory output, as well as the latched ALU result to be written into the register file. Right? And that's the idea, basically. And this is the other thing over here. Whenever you're doing an add, at least R-type add, you need to have a second register source to be selected. And now you need to make sure your signals over here are correctly specified so that you pick the second register source. Okay, BEQ is also similar. I'll go through this again relatively quickly. You need to calculate the branch address. How do you calculate it? Well, you can actually calculate it over here in the ALU again, because branch doesn't use the ALU for some other purpose. You calculate the branch address in the ALU, and if the branch is taken, you use that target address and load it into the program counter, basically. You need to add the data path elements to be able to do all of that. Okay. Now let's construct the multi-cycle control logic. And you can keep doing this, basically. I've added many instructions, but you can keep adding more instructions by adding data path elements as well as control signals. And this is the complete multi-cycle processor for equivalent of the single cycle processor that we have examined. Now let's construct the multi-cycle control logic quickly. Basically, we're going to construct this control unit. We have a finite state machine that takes opcode as input and also function as input in this decoder over here. And that generates the multiplexer select signals as well as register enable or memory enable signals over here. And you also output that to ALU up so that you can control the ALU over here. So basically, we're going to construct the finite state machine. You kind of see an example earlier. In the fetch state, you need to set the control signals so that you can fetch. I'm not going to look at all control signals, but this picture shows you how to set the control signals such that you can take the program counter and put it into this register and do no harm in any other part. For example, don't write to the register, don't write to memory, etc. So you need to set the control signals. That's our fetch state. After fetch state, what do you go into? Decode. And decode basically it takes this register that we latched, which is the instruction, and generates the control signals and does no harm over here. So you need to set the control signals over here again accordingly. And then after decode, if it's a load word or store word, you jump to a memory address calculation state. And memory address calculation, you need to calculate it based on the specification of the instruction. You set the control signals accordingly. Here, I don't write the control signals because it's specified over here. And you can go through it and make sure that it is correct. Actually, it is correct. This is from your book also. So basically, you go through step by step to execute an instruction. As you can see, these are some important control signals that are highlighted over here so that you can calculate the memory address in the ALU. And then the next stage is memory read for load word. Actually, and then the next stage is write back to the destination register in load word. And then you go to the fetch state so that you can fetch the next instruction. So this is how you execute load word. How do you execute store word? Store word goes here basically. As opposed to doing memory read, you do a memory write, and then you're done. You set the control signals accordingly in your data path such that you do memory write, and then the next state after that is fetch of the next instruction. R-type instructions, well, when you decode them, you figure out their R-type. The next state is execute. You set the control signals accordingly such that execution happens in the data path that I showed you earlier. And then the next state is write back to the register file. But you can see that everything happens in different clock cycles, right? These different states happen in different clock cycles clearly. And then you go to the next instruction. Branch equal, we covered. So you can see that if the opcode is branch equal, you execute everything in one cycle over here, and then you go to the next fetch state over here. And this is the complete FSM. It doesn't include jump. So assume that you have this finite state machine, and now you want to add some more functionality. You want to add some more instructions. Let's say we want to add immediate. You basically extend the state machine. After you decode, you figure out that it's an add I. You add an execute stage, you add a write back stage, and you set the control signals accordingly. That's the beauty of this machine, basically. You need to extend the finite state machine to execute different instructions, and then you set the control signals accordingly. You may need to add data path elements also clearly. Okay, let's take a look at jump, which is our favorite. It's a simple instruction, but again, once you decode the instruction, you figure out it's a jump. You need to basically execute the jump. And actually, I don't show the data path elements, but you can find the data path elements. Okay, here's it. My computer is somehow, okay, sorry about it. And I actually also had, so to be able to execute jump over here, you need to add the jump address calculation logic, which is sign extended 26-bit immediate, actually 26-bit immediate shifted left by 2. And you need to add another multiplexer to support that jump, in addition to a state that you need to add over here. So basically, this is a beautiful paradigm where you can keep adding new states as you add more instructions to a machine, and also need to fix the data path so that they can support the states that you've added clearly. So this is our review. We're basically done with the multi-cycle MIPS FSM. So there are shortcomings of this design. For example, here we're assuming memory takes 1 cycle, but that's easy to fix actually. We assume memory takes 1 cycle. What if it doesn't take 1 cycle? What if it takes 100 cycles? Well, memory tells you when it's ready. So you stay in the memory access state until memory tells you that it's done. Basically, every clock cycle you check, is memory done? No, you stay in the same state, which is the memory access state. Every clock cycle you do this checking until memory tells you I'm done, you stay in that state. It could be 100 cycles, it could be 1,000 cycles, it could be million cycles. You're in the same state waiting for memory to tell you I'm done. Once it says I'm done, you go to the next state, basically. That's the beauty of this. You don't need to design your clock cycle time to take 1 million nanoseconds, for example. Right? Okay, so that's the idea. I kind of said this basically. Stay in the same memory access state until memory returns the data. So you need a memory ready bits input to the control logic. So there's another example, microprogram multi-cycle microarchitecture in your book, which is Pat and Patel. Actually in Appendix C, which you can find online in the course website. I'd recommend you take a look at it. I'm not going to make you responsible for it. It's also a beautiful design in LC3, but we don't have time to cover it. And if you're really interested in microprogram designs, you can actually watch lectures as well. Okay, that brings me to the end. Have a nice weekend, and I'll see you next week. Okay, let me actually turn off the live stream. Nope, if I can. What should I do? Turn off the live stream?